Good morning, everybody. My name is Eddine, a PhD student at University of Ain Timushan. I'm going to speak about interesting subject which titled Exchange Correlation and the Spin-orbit coupling effect in transparent conductor ab initio study. So the main outline of this case study is introduction, half Husserl alloys with 18 valence electrons, computational methodology, a result discussion, and finally we have conclusion and perspective. One of the principal challenges facing the world in energy at present is the driver research for alternative energy resources such as the thermoelectric materials, because the thermoelectric effects enable direct conversion from thermal to electrical energy. In the last decade, hostile compounds have attracted significant research attention for their thermoelectric property, despite their chemical similarity. Different compounds within the class of material exhibit very different electrical and thermal transfer properties. Hostile compounds are among the best known anchor metallic compounds, such as full and half hostile. The composition of hostile compounds are represented as shown in this figure by the chemical formula X2YZ and XYZ for full and half hostile respectively, where X and Y atoms are transition or noble metals, and Z is a main group element. So the two compounds crystallize in cubic structure, with the two different typical structure and space group as shown in this slide. We notice that half hostile structure can be obtained if one of the two sublattice is vacant. One of these compounds that we study here is TaArSb, which classified within transparent conductor. These three atoms are part of fourth and fifth group in periodic table. Antimony, titanium, iridium were the alloyed of many important materials, such as thermoelectric material because of its interesting physical property. This figure shows the crystalline structure of our compound, and it's clear that it has half hostile structure, where we can describe it by interpenetration of three-phase central cubic sublattice, where each one of them is occupied by atom titanium, iridium, and antimony with the following weight of position. Our aim in this present work is studying exchange correlation and the spin-orbit coupling effects on our compounds, such as structural property by calculation lattice parameter correspond to each functional approximation, as well as electronic property by calculation band structure and gap energy. So before going to the results obtained in this work, the following slide represents the computational methodology of our study. The methodology used in this work is ab initio study with plane wave and pseudo-potential method, were performed by using quantum specification which implements density functional theory. We use the three approximations of exchange correlation, such as GGA plus U, and meta-GGA functional, with and without inclusion of the spin-orbit coupling. The most successful and widely used for GGA approximation called PDE. On the other hand, the recently developed meta-GGA called scan functional. For the pseudo-potential method, we use the two types. The first one is ultra-soft pseudo-potential for PDE, and the second one is non-conservative pseudo-potential for scan functional. So to optimize a structural parameter, we have the cutoff for kinetic energy was fixed to 50 radian, as well as the Zoll-Breuil integration was performed using Noether's back sham with tanky point mesh. For studying the structural property, the lattice parameter and bulk model have been calculated by computing the total energy for different volumes and fitted with Marnagan equation of the state. So this figure shows the variation of energy using PBE, PBE plus U, and the scan functional with and without including of spin orbit coupling. The optimized volume in each functional approximation correspond to the following lattice parameter as shown in this table. So the results show good agreement with the previous theoretical data. On the other hand, we notice that the mesh parameter decreases when we go from PBE to PBE plus U to scan functional. Moreover, we notice that spin orbit effects is almost neglected. Despite the functional PBE plus U plus spin orbit coupling better describes our compound structure, where the value of mesh parameter closer to the theoretical data value. But generally, the study of structural propriety shows no important effects of spin orbital on the mesh parameter and considered as neglected. After studying structural property, this part represents electronic property of our compound, such as band structure and gap energy. The following figures shows the band structure of PAAR-SD using a PBE, PBE plus U, and the scan functional with and without spin orbit coupling, where the black line for the presence of spin orbit coupling and the red line for absence of spin orbit coupling. So it's clear that band structure calculation shows the semiconductor behavior of the material with and direct band gap at the same location and a Brillouin zone for all approximation of exchange correlation. Moreover, we notice that spin orbit coupling decreases the band gap and causes the degenerate band to split the Higgs symmetry direction in the Brillouin zone. The band gap values at Higgs symmetry point with other theoretical data are listed in this table. So as we said, it's clear that our compound is a semiconductor from the values calculated for all approximation of exchange correlation. The spin orbit coupling effect is more important in the case of a scan functional, where the difference between gap energy in the presence of spin orbit coupling minus gap energy in the absence of the spin orbit coupling equals 0.37 electron volts. This figure shows the gap energy values obtained with a different exchange correlation approximation, with and without inclusion of a spin orbit coupling. This coupling decreases the band gap for each approximation, especially in the case of scan functional with a spin orbit coupling. Finally, our aim in this work was making a quantitative and qualitative study of the spin orbit effect on structural and electronic property of this compound, which is classified as a transparent conductor using a different approximation of exchange correlation, where we found that the spin orbit coupling effect is almost neglected in structural property such as lattice parameter. On the other hand, has an important role in the electronic property, such as band structure and gap energy. So, in the future, we look forward to studying the contribution of atoms on each approximation used previously, so as to further understand the physical property of this compound. That's what we have until now, and thank you for your attention.